Hey everyone, buckle up, because today we're diving headfirst into the world of AI.
Specifically,
a fascinating new approach to building, you could say, brains for robots.
Okay, I'm intrigued.
Imagine robots that learn like we do, adapting in real time to whatever curveballs life throws their way. That's the promise of liquid time constant networks.
LTCs for short.
Exactly, LTCs for short.
So what's the secret sauce? What makes these LTCs so special?
Well, what's really cool is that they process information in continuous time.
Continuous time, you mean like constantly, not in chunks?
Exactly, much like our own brains, actually. See, most AI systems out there analyze data in separate chunks. It's like looking at individual frames in a movie.
Right.
But LTCs, they experience time as a constant flow, just like you and I do in the real world.
Interesting. So it's less like a slideshow and more like, well, real life.
Precisely. It's like the difference between checking your watch every minute versus having this innate sense of time passing.
Okay, I'm starting to see the appeal here. But what does that actually mean for, like, how these networks learn and adapt?
Well, think about it this way. Imagine you're trying to teach a robot to ride a bike, right? Using traditional AI, you'd have to feed it tons of individual snapshots of the process.
Hoping it picks up on all the little details.
Exactly, hoping it picks up on the subtle adjustments needed to stay upright. But with LTCs, it's more like the robot is experiencing the act of balancing in real time, constantly adjusting its movements based on, the continuous feedback from the environment.
So instead of learning from static images, it's learning from the flow, the actual feeling of riding a bike.
Now you're getting it. That's exactly it.
No wonder the researchers behind LTCs are seeing such promising results. This is a big deal, isn't it?
Oh, absolutely. This continuous time approach makes LTCs incredibly good at dealing with unpredictable scenarios. In fact, one of the things that really stood out to me in the research was how these networks handle sudden changes or unexpected inputs.
Oh. What happens with these LTCs when things get a little crazy? Well, traditional AI systems, the ones that work in those discrete chunks, they tend to, how do I put it? They get easily thrown off.
Thrown off by what?
By big, unexpected inputs. Their outputs can essentially explode, becoming totally unreliable. Imagine that happening with, like, a self-driving car.
Okay, yeah, I definitely don't want my self-driving car having a meltdown because, like, a pigeon decided to cross the road at the wrong moment.
Exactly. That's the thing with LTCs. They're far more resilient.
Resilient how?
They've got this built-in adaptability. They're time constant. Basically, how quickly they react to changes, it adjusts.
It adjusts on its own.
Dynamically. Based on the information they're receiving, it's pretty slick.
So it's like having, what, shock absorbers for their artificial brains?
Yeah.
They can handle those unexpected bumps in the road?
That's a great way to put it. That's why LTCs are so exciting, especially for, like, robotics or anything that requires real-time decision-making in these constantly changing environments.
This is already blowing my mind, but, I'm curious about how we even begin to measure how powerful these networks really are. I mean, the research papers we dove into kept mentioning this term, expressivity. What does that even mean in the context of, like, AI?
It's a good question. In simple terms, expressivity, it refers to the complexity of patterns a network can represent. Think of it like this. Imagine you're drawing a map of a city, right?
Okay, I'm following.
A simple network, one with low expressivity, it might only be able to represent the main streets.
The main streets, got it.
But a more expressive network, like an LTC, it could capture all the winding alleys, the parks, those hidden corners, giving you a much richer understanding of that whole urban landscape.
So a more expressive network can learn those more intricate relationships in the data, leading to what? More accurate predictions, better decision-making.
Exactly. And one way researchers measure this is through something called a trajectory length.
Trajectory length.
It's basically a way to visualize how much complexity a network can handle.
I need an example.
All right, picture this. You feed the network a circular path as input.
Okay.
A simple network might only be able to output, a pretty crude approximation of that circle.
Right.
But an LTC, with its higher expressivity, it could reproduce that circular trajectory with, like, way more accuracy and detail.
It's like the difference between drawing a circle with, a compass versus sketching it freehand. The LTC is capturing those subtle nuances that those simpler models just completely miss.
You're getting it. And that's what the research shows too. In their experiments, LTCs, they consistently outperformed other state-of-the-art models in these tasks that require, well, this kind of nuanced understanding of patterns.
Give me an example. What kind of tasks?
They looked at everything from like predicting human actions based on motion sensor data to things like forecasting ozone levels. And get this, in 4 out of the 7 tasks they tested, LTCs came out on top.
Okay, now we're talking. But how much better are we talking here? What kind of improvements did they actually see with these LTCs?
We're not talking about small incremental improvements here. No. In some cases, LTCs showed, get this, a 70% improvement in accuracy compared to existing models. That's huge, especially in fields where even small gains can have a huge impact.
70%? Are you serious? That's like going from using a blurry, outdated GPS to having this crystal clear, real-time navigation system that knows every shortcut and every traffic jam in the city.
It's a good analogy. It highlights how LTCs could revolutionize fields like robotics, self-driving cars, even healthcare. Anywhere that precise, real-time analysis is absolutely crucial.
Okay, so we've talked about how LTCs work, their ability to handle those unpredictable situations, and their really impressive performance in those real-world tasks. But where does it all go from here? What's next? What's the big picture when it comes to, like, the future of this technology?
Now that is the million-dollar question. While LTCs are still relatively new, I mean, they're just babies in a lot of ways, but their potential, it's immense. Their stability and expressivity make them ideal for anything that requires real-time adaptation. Imagine a robot that can learn and, what's more, adjust its movements on the fly, even in a constantly changing environment.
That'd be incredible. No more pre-programmed robots that just fall apart the second something unexpected happens.
Exactly. But it goes even deeper than that. Remember how we talked about expressivity and how LTCs can capture those complex patterns?
Yeah.
Well, that capability, it opens the door to a whole new level of understanding in AI.
Oh. Tell me more. This is where it gets really interesting.
See, LTCs, they have this unique connection to something called dynamic causal models.
Dynamic causal models. Okay, now you're just using big words to sound smart. What are those?
I'm not. Okay, so these models, they're all about understanding cause and effect in complex systems.
Oh.
And because LTCs operate in continuous time, they're uniquely suited to take advantage of this type of modeling. It's a game changer.
So not only could robots react better in real time, but they could also start to, understand why things are happening the way they are. Like they could start to actually make sense of the world around them, not just react to it.
You got it. It's like the difference between, let's say, seeing a ball rolling down a hill and understanding the forces of gravity and friction that are governing its motion. With LTCs, we're moving beyond simple pattern recognition towards like a deeper, more fundamental understanding of how the world works.
Okay, I'm officially geeking out over here. This is like seriously amazing. But before we get too carried away, we have to address the elephant in the room. The research papers did mention that all this power and sophistication, it comes at a cost.
Right. Oh, you're talking about the resources. It's a crucial point. While LTCs offer incredible potential, they do come with certain trade-offs, particularly when it comes to computational resources.
So more power, more responsibility. Or in this case, more computing power and memory required.
Yeah.
What are we talking about here specifically?
Well, LTCs, they are more complex than those traditional AI models. They need, more memory to store information and more processing power to, crunch through all those continuous calculations. It's kind of like the difference between, say, sketching a simple map on a napkin versus rendering a detailed 3D model of a city, the 3D model. That's going to demand a lot more computational muscle.
That makes sense. So we're essentially trading off, increased complexity for greater power and accuracy. But is it a worthwhile trade-off? I mean, how big of a hurdle are these computational demands, really?
It's a balancing act, that's for sure, right now. These resource constraints, they're definitely something researchers are, grappling with. But on the bright side, computing power, it keeps advancing at this incredible pace. What might seem like a major hurdle today might be, a trivial matter in the not-too-distant future.
That's a really good point. It's like how those, bulky room-sized computers from way back when, they eventually shrunk down to those smartphones we carry in our pockets today. What seemed impossible back then is now, totally commonplace.
Exactly. And who even knows what breakthroughs are right around the corner, right? Quantum computing, new bio-inspired hardware. I mean, these kinds of advancements could totally change the game when it comes to the resources we have available for AI.
So while these limitations exist today, they're not necessarily deal breakers in the long run.
Precisely. And even with these limitations we have today, remember, the researchers were still able to get those remarkable results. That 70% accuracy jump, for instance. Imagine what's possible as this technology, grows up a bit, as those computational hurdles shrink.
Now, that is an exciting thought. So what does all of this mean for you, dear listener? Why should you care about these, what do we call them, artificial brains, with their continuous calculations and whatnot?
Here's the thing, AI. It's not some futuristic fantasy anymore. It's here, it's evolving crazy fast, and it's increasingly intertwined with our everyday lives. From those recommendations you see online to those traffic updates on your commute, AI is already shaping your world, whether you realize it or not.
And as AI gets more sophisticated, more capable, it's not enough to just, interact with it passively. We need to understand it.
100%. Understanding how AI works, its potential, and yes, its limitations, that's crucial for all of us. It gives us the power to engage in those informed discussions about the future we're building, all of us, together. A future where AI isn't something to be afraid of, but a tool to be understood, shaped, and used responsibly for the betterment of, humanity.
Beautifully said. As you go about your day-to-day, take a moment to think about all those processes happening in continuous time all around you. The ebb and flow of traffic, the ups and downs of the stock market, even those subtle changes in your own body as you move through the world. Now imagine AI that can not only analyze all those intricate patterns, but also, and here's the kicker, grasp the underlying forces that are actually driving them. The possibilities, as they say, are truly limitless. Thanks for joining us on this deep dive. Until next time, keep those brains engaged and those questions coming.